Someone, you can see the screen, isn't it? Okay. So what we have learned so far is the fundamentals of the compiler. However, we haven't completely seen how the compiler actually stores the information. Because if you have noticed so far, we do have, let's say, the symbol tables onto the, like we do store the informations of different scopes into the symbol table. That's the data structure we are actually following. However, how this data structure is being implemented. So in general, or in usual cases, it is actually implemented in the stack or in stacked formats. The symbol tables are the informations, the required function parameters, and whatever there are, these are actually stored in stacks. So that will be our this session, where we will be actually sort of like going into the world or having a peep into the world of how this stack is being implemented in allocating the spaces required for the symbol table, at the same time the like storing of the information in different scopes. Now, like whatever compilers there are for the feature of for the features of or for the uses of these three things, which are procedures. Now procedures are basically, like if you have done the microprocessor or assembler language course, you would have seen the concept of procedure there. So procedures are similar to function, where you call a procedure and the pointer goes from where you have called the procedure, from that place to the position of the procedure. It executes the sequence of codes and then returns the pointers or the control to the point immediately after the call instruction. So if you have, like if you remember, in assembly code, we have a call instruction that's a call to some proc1. And when this procedure is called from, let's say, line number 31, after the procedure gets executed, it returns the control to the next possible instruction. So the next possible instruction is stored in the instruction pointer. And then the instruction pointer call like returns back the control to the caller, the position where, or from the position where the call was being made. Now, that's basically what procedure refers to. And there is also the usual cases which we implement. These are functions, and in some programming languages, like it is mentioned as what? Methods. This, like the structure or the procedure, the system or the process, they like all of them implement is sort of same. These are user-defined units which actually sort of manages like all of the part of the execution or all of the part of the, let's say, program while runtime. Now, why am I saying this runtime? Because remember, while executing, this function gets called, isn't it? This method gets called while executing. When we declare a function and when we call this function from somewhere, when we execute the program, at that moment, this function gets executed or this function gets called, isn't it? So that means during execution is basically what? During execution is basically during runtime. So while we are running the program itself. Now, when the procedure is basically called, it has some, if it has some local variables. So let's say there is this procedure and it has int a, int b, like these are the local variables defined for this procedure. So these procedures, these local variables will be basically stored onto the stack. So this is the stack. And before, let's say this procedure also calls some other procedure. Inside this procedure, there's some other like procedure call. this is proc, and inside that we are calling proc1. In that case, the control or the controller will point the control point to some address where the proc2 is or proc1 is located. However, we were calling this procedure 1 from inside this proc procedure, isn't it? And inside this proc procedure, we do have some previously declared variables. Now, once we go to the proc1, we do not require this like local variables. Like we do not require the information of these local variables, isn't it? When we are inside this proc1, we are not requiring the information regarding these local variables because we won't be using them. However, once this proc1 gets executed completely and when the return is made, it comes back to this point, isn't it? Now, when it comes back to this point, and if it performs this operation a equals to 5, and if it doesn't know the information of a, then it will be a great problem, a big problem. Now, that refers that we are supposed to store this information a and b. Now, when we are calling this like proc1, we only have the information of proc1 now. We are discarding or getting rid of this information. But getting rid of this information, if there exists some operation after the call function, which requires such declaration values, in that scenario, we won't be recognizing this a anymore. So if let's say we are discarding the value of a and b when we are calling proc1, then what's the problem? The problem will be if there is a expression or statement where a is being used after the return call, then we won't be recognizing this a anymore. Hence, what we need to do before making this call, we have to store the information in order to retain the state before the call was made. Hence, these local variables will be stored inside let's say the data the data set or the space for this proc or the proc procedure. So here the values of a and b will be stored, and then we will basically make a call for proc1, and this will be now new stack or new region for this proc1 where the proc1's local variables and proc1's values will be saved. Now, once this portion gets executed completely, this stack, the point which is this is the topmost value. Remember, in our case, in the compiler's case, the stack will be upside down. So the top value will be the bottom one, okay? So this stack will now get filled in the reverse order or in the downward manner. So whatever we will be pushing inside the stack, the value will be stored at the bottom part. Hence, the topmost value is basically at the bottom. So once this proc1 gets executed, this topmost value, which is over here, this will be popped. So this will get popped, leaving us with what? The results of proc1 now. So we are now restoring the value of proc1. So this is how basically the procedures like functionality matters and how stack is being allocated. Because remember, the symbol table is a concept, the data structure we are using. However, we are not, like we need to place that symbol table into some memory, into some location, into some space. Now, symbol table is basically a structure we are following. However, in order to store this in this structure, we require a space, isn't it? There's these two things. One is structure, and another is space. Stack is the space onto which we will be placing this structure we are previously declaring. Okay. Now, I will be trying to introduce this term, which is basically the activation tree. Now, what is this activation tree? Let's try to dig deeper. Oh, by the way, the process we just saw for procedure, it follows the functions and the methods follow the same pattern. This information is stored in the very similar way, okay? I was talking about the activation tree. Now, what is activation tree basically? This activation could be used as a synonym to execution. Execution. Now things will be much more simpler for you. So whenever you will, or whenever you see this activation key word being used, or I'm referring to this activation keyword, go back to this meaning where I have written and change that activation keyword with this keyword, which is execution. Now it will make sense to you more. So what actually happens? Let's see. For, like, in order to have the stack being implemented, or in order to make this feasible, we have activation of the procedures. Remember, whenever I'm using this activation keyword, just replace the activation with execution. Then you'll be able to understand what am I trying to say. So what did I say just now? Activation of procedure. So activation of, why did it freeze? Oh my God. Reconnect. Let's try. Okay, so they're kicking me out from this board. Let me use this board. Okay, so hello, Salman. By the way, like, am I audible? Like, or did I get disconnected? Okay, I'm audible, but now I'm listening to you in a crackling voice, like this breaking. So let's see. Yeah, I think we're here. Okay, let's see how this activation term works. So I mentioned we have this activation of procedure, and we will represent this in the activation tree. Now, I have mentioned just before, like just a bit before, that whenever I have this activation keyword, just replace it with the execution keyword. That will make more sense. So now here we have two of these keywords used, activation. If we say, instead of activation, we say execution of procedure, now it will make sense. Okay, we are now executing the procedures. That is basically known as the activation of the procedure. Now, in order to implement this activation tree, let's take an example. So the example I'll be following is basically this part. So let me write the instruction. So let's say int a of 11, then I have a void function. Like, I'm going to implement the quick sort. So I read array, and inside that I have some, like, instructions along with, like, what values to, or what array to, like, this array to be written. So there will be some other lines. I'm just trying to make this as simpler as possible, like as small as possible, because I don't need to write those redundant parts because I'm only focused on how these procedures or how these functions are being called and how this activation tree is being made. So I have this partition function where I will be passing two parameters, int m, int n. Again, there will be the partitioning algorithm inside. I won't be writing that here. And finally, there will be this quicksort function. Also there, I will be passing the m parameter and the n parameter. And again, here we'll be quick sorting, but let's look, this is very, like, this only contains 4 lines. So let me write those parts. So we initialize this I, and we check whether n is greater than m or not. If n is greater than m or not, if that's the case, then I is basically the partitioning. That means that the index we are working with, I is basically the index. The partition, like sort of, you can say the pivotal point. So partitioning, and the pivotal point will be returned from the partition function. And after that, we will be basically quick sorting for from m up until I minus 1 and from I plus 1 to the nth value. So quick sort, we have from m to I minus 1, and then we have quick sort from I plus 1 up until n. And hence this if condition ends and this quick sort function also ends. And finally, we'll be basically calling the quick sort function from this main function, where we'll at first call the read array because we will be reading the array, the global array. So we'll be reading the global array. Then we'll be setting the sentinel. The sentinels is basically setting up the like boundary values. So these will be the very like maximum possible values and the minimum possible values, so that when we implement the quick sort, it does not actually process or sort of like overflows to the next memory location, or it doesn't like it stays within the limit. It stays from index 1 to 9 of the array. Since like if you notice in this array, we're declaring this array of 11 elements. So we will be setting basically the 0th number element as the minimum value possible, which should be actually much less than what the values is inside within 1 to 9, from array position 1 to 9. And the 10th position will be the maximum value, which is larger than whatever value is within this array. And finally, we call the quicksort algorithm, passing the index from 1 to 9. And let's say we return a value of 0. Okay, let's try to make this a void function. So things will be much more simpler, so that we don't have to return anything now. So let's say it's a void main function. And finally, this is the function. So if you now notice what we did here, so we have that first, like in the global scope, we are declaring A of 11 array. Then we have a read array function. Then we have a partition function, and we have a quicksort function. Finally, the main function. And within the main function, we are calling at first the read array. And after that, we are calling the quicksort array. I mean, read array function, and then the quicksort array function. And within that, we are actually setting the sentinels. Sentinels is basically the upper limit and the lower limits. Now, if that's the case so far, then like how, like what are the cases, or what are the common cases that could arise? Now, one of the cases basically, before like solving this, one of the cases for this activation to perform. So let's say, there's this procedure P, there's this procedure P, and let's say like we are this procedure P, within this procedure P, the procedure Q gets called. So call Q. So Q is another procedure. Because so basically P is calling Q inside it. Now the activation of this Q basically happens or gets completely executed. That means it should end its execution even before P could get executed, or the activation of P ends. So what does this mean? If you if you notice, let's say the instruction starts from here and then it goes to procedure P. So when we are in procedure P, the scope for P starts, isn't it? Now, after that, inside P, we are calling Q. Now, when we are calling Q, has the execution of P ended? No, the P will end when, let's say if we have some other code and this curly brace ends, let's say. After this last line, the execution of P will be ending. That means the activation of P will be ending after this last line. Hence, if let's say we have only these two lines, for the first one is entering the procedure P, and then the next line is calling Q. So what this makes you understand? This makes you understand that before ending the activation region of P, Q must end its activation. So when we are calling Q, we get to go to this procedure Q. Whatever is inside Q, everything, the execution of every of this thing must end at first. Only then we can return back and execute this P completely. So the execution unit of P will only then, after the execution of Q ends, can end P. So if I try to make the words more simpler, the execution of P will end after the execution of after the ending of the execution of Q. So if this is P, P have this region, let's say, and within that Q at first have to finish, then only P can come back. So if you see it on the stacks format, so at first we go to the procedure P, so that will be stored onto the stack. Then we call Q. So Q will be there. Now, which one is the topmost element? The Q is the topmost element. So even before before executing Q completely, we won't be able to pop this Q from the stack. And if we are not able to pop this Q from the stack, then we won't be able to get to P and pop the P from the stack. Hence, even before trying to pop or eliminate or end the activation of P, we have to work. We have to be done with the execution or activation of Q. That's what we can say, what I'm trying to portray here. Now, as I was mentioning, there are some scenarios where the cases can what the cases can be, or there's these scenarios where the activation actually handles in different ways. The first one is the activation of Q terminus normally. So termination of Q is in the normal process. So what is happening here is basically, let's say we have this P or the procedure of P, and then we have inside that we call the procedure Q in the same manner we did here. Okay. Now after Q ends, the pointer returns to P, and finally P also ends. Hence, what happened here? The termination of Q happened normally. There was no issue with that. The second point was, or the second case could be, is that for the execution of Q, the execution of procedure Q, let's say, or from where Q is being called, so this is called, and Q actually Q simply aborts. After Q has been called, Q simply aborts. That means some error happened. Let's say, situation occurred which Q cannot perform, and this was called from P. So P called Q, and inside Q, some the Q is directly aborted. The whatever procedure was Q supposed to perform. And what happens is it becomes impossible for this execution to continue. So after abort, so impossible or disruption in continuation of execution. Continuation of execution. Sorry. Why can't I write it? I have forgotten the spelling. Execution, yeah. Execution. That's what happens as Q ends, P ends simultaneously. So P, let's say P starts from here, and then it calls Q from here. Then the context switches to Q, and Q starts. And even before Q gets started, Q aborts. So Q ends at this moment. P also ends at this moment. So P and Q simultaneously end. While on the first case, what happened? P started, from there Q hands over, and Q ends. Then again, the control flows back to P and then ends here. However, over here, once P gets executed, like P is executed, like execution of P starts, it hands over the control to Q. Q aborts, and Q and P simultaneously like closes their execution. Okay, so that's basically the second type of scenario. The third type of scenario is basically where, let's say, some exception handling occurs. So if you have in operating system, we see some sort of exception handler, isn't it? So if some sort of some interrupts occurred, and we have the hardware of the system perform that interrupt based on the priority. Now, in this case also, some exception occurred while Q was called from P. So P called Q, some exception occurred, and that caused this Q to terminate. This caused this Q to terminate. So if Q gets terminated, then Q cannot actually handle this exception. Due to this exception, Q cannot handle this exception, hence Q gets terminated. Now, the control returns back to whom? P. Now, P might be able to handle this exception, might not be able to handle this exception. So what happens? So in this case, the activation of Q, we just saw, it terminated while the Q actually gets continued. So P starts, calls Q, Q is trying to execute, exception occurs, it gets terminated, and P continues its execution, though it's not necessary that it will return back to the point where Q was called from. So let's say we are inside this procedure P, and we have, let's say, declared int A, int B, and there after that call Q. Now, after, like in normal cases, what happens? The call, like after this call has been made, the procedure Q gets executed, and it returns back to the point from where Q was called, isn't it? However, in this scenario, it is not necessary that when exception occurred and Q gets terminated, this will return the execution or the pointer to this point where the Q was called in first place. So from onto this place, the Q will be, or the pointer will be returned. This is not necessary. Rather, the pointer could return into this position or some other position after like certain jump. So that is also a possibility. Okay, this resulted because of this exception. Some like anonymous or unhandleable exception or error occurred. Okay, hence such scenario actually took place. Otherwise, this was like not normal. Now, let's try to have or plot the activation key. Now, before having the activation key, if you see here, what will happen? Let's try to see in this code. Let's try to see the sequence that will actually occur. At first, when we are trying to, like in the context of C language, like do this line gets executed first or this line gets executed first, or this array gets executed first, or this function gets executed first. If you remember, in the context of C, the function main gets executed at the very beginning, isn't it? So what will happen is basically we will enter the main region at first. After entering the main region, we enter which region? Here you can see we try to enter the read array region. So enter the read array function. We will make entry to that region. Once we enter to this read array, it will start or enter this region, and after execution, it will return back, isn't it? Hence, it needs to end this read array. So if you now focus here, once we call this read array, and after that, we are, let's say, calling this quicksort. So even before we are able to call this or make this call function, make this quicksort call, sorry, even before we are able to make a call to the quicksort function, we have to do what? We have to end this read array function. Hence, I'm saying the end of read array is happening here. After that, we are entering this quicksort region. So we are calling this quicksort after the read array occurred. So quicksort, and inside that quicksort, if we come here, you see at first we call this partition function. So inside this, we enter to the partition function. And after the partition function, we have another quicksort call. However, before being able to call the quicksort function again, we have to do what? We have to end this partition function, isn't it? So we enter this the partition function, we exit this partition function. So another keyword, instead of writing this end, we can write actually exit. However, in the book, it is written leave. So these are the same thing, exit or leave. So I will be writing exit, the exit keyword here. So we enter the partition function, and then we exit the partition function. And after exiting the partition function, we will simply enter this quicksort. Okay, so this quicksort will be entered. So sorry, we will enter the quicksort function with certain parameters. Now, let's say this parameter is 1,9, and then we have for partition also on 1,9. And for this quicksort, after that, let's say 1,3. Like these are the parameters I'm passing. Now, once we enter this quicksort, which is basically again starting from here, we have what? We enter this quicksort. Inside this quicksort, the first thing is entering this partition. So now let's see, this is happening what? A recursive procedure. So enter partition with, let's say, the parameters 1,3. And we also have to exit this partition before able to call the next quicksort. So and exit partition 1,3, let's say. And then we can again enter a quicksort. And that quicksort will do what? That quicksort will basically call again another partition function. And this will continue. This will go on until we're done with the quicksort. And finally, we will have the exiting statements. Why? Because after this quicksort, one after another, we will exit from this quicksort. Then again, we will exit from this mother quicksort, and then again from the mother's quicksort, and that will continue, isn't it? Because we entered this quicksort. This quicksort needs to exit somewhere, isn't it? Exit quicksort needs to happen to get out of this quicksort. Why? Because there is another quicksort which we entered, and that region, in order to be exiting from this region, we have to exit this quicksort at first. Okay, so this is how the recursive nature actually works. Now, this will be very important in order to draw our activation tree. So how should we draw the activation tree? Let me at first erase these portions. So I will try to like make things much more simpler. So let's represent this main with the M value or M keyword, the quick sort with Q and partition as P and read array as R. So if we now try to draw the activation tree, it will look something like this. We have like enter the M region, the main function. The main function has a read array, so R for read array. And on after that, we have what? The quick sort. So Q, and let's say inside that we passed 1, 9. And inside this quick sort, the first thing we had called was what? The partition function. Onto that, we passed the 1, 9 parameter. And then we have what? We have a Q, which is quick sort. And that quick sort is, let's say, from partitioning, we got 4 as the result. So it went up until 1 to 4 minus 1, which is 3. And for the next quick sort, which is this one, this will be basically what? 4 plus 1, which is 5, 9. So Q 4, 9. And this partition has no more, let's say, recursion. If you notice here, this partition has no more recursion. However, again, this quick sort has more recursion, which is first parameter as P, or the partition of 1 to 3. And let's say the next, we get the return value as 1. So we will pass Q of 1 up until 1 minus 1, so which is 0. The next quick sort function will have from 1 plus 1, which is 2 up until, let's say, 3. So this is this portion. And again, like this is up until quick sort 1 to 0. So this is the M value, this is the N value. And once it is checked that this N is greater than M, we will do this work. Otherwise, we won't do anymore, like we won't be calling any more quick sort. So hence, this gets eliminated since N is smaller than M. For this, N is bigger than M. So again, from here, we will get to call the P 2 to 3, and the partition will return Q 2 to 1 and Q 3 to 3. In this manner, it will go on. And from here, if you notice, again, N is less than M, so no more calling. And here, N is equals to M, so N is not greater than M. So again, this will stop up until this much. And we return back to this portion. So this Q will have a P from 4 to 9. And this, let's say, this will return basically as up until, let's say, the value of 6. So we start from, we simply say, no, sorry, this isn't 4, this is 5. It's 5, so 5 to 9. So it returned the value of, let's say, 6. So the Q will be basically 5 up until 6 minus 1, which is 5. So 5, 5. And the right Q quick sort will be from 7. 6 plus 1 is 7, 7 to 9. And since N is equals to M, this won't be calling anymore. And this Q will call the partition function, and that will have 7, 9. This returns, let's say, the value 8. So we will call quick sort 7 up until 8 minus 1, which is 7. And quick sort of 8 plus 1, it is 9, 9 up until 9. And again, these are M and N are equal, and M and N are equal. And so we won't be calling any more quick sort, and our quick sort function has been covered. Now, if you see this tree over here, this is basically the activation tree. Now, this activation tree refers to that. Let's say this Q of 1, 3 is alive. If this is alive, then this Q1, 9 and this M are also stored in the stack, and they're alive. They haven't finished their execution. However, this P have already finished its execution. Why? Because before able to learn, or like execute this Q of 1, 3, we have to execute, like finish the execution of P1, 3. This could be followed from Sorry, I have erased that part. So we entered this P region, then we exited the P region, and then we entered this Q region. Once we, again, also in this case, we entered this Q region. From there, we entered this P region, we exited this Q region, we entered this Q region. However, we haven't yet exited this Q. Hence, in order to execute this Q, we have to parse this entire tree. Now, if you focus, if you try to see, it is basically doing what? This is basically doing post-order traversal. Post-order traversal. So post-order traversal happens for what? For the exiting or elimination of the activation node, the activation of the node. Now, the sequence of the procedure calls to make, in this case, let's say, like one after another, which we saw initially, the call function, the initial calls that are basically pre-ordered. Now, why is it so? If you have noticed, once we, let's say, enter main, so we are entering main. So I'm representing main with M. From that M, we are entering what? Enter R, exit R. Now, if you see here, for calling purposes, okay, for the sequence of calling, what happens? We entered M, then we entered what? R. After that, like, entered R means calling R, then we are exiting R, then we are calling Q, then we are calling P, exiting P, then calling Q, exiting Q, calling this Q, exiting Q, and before exiting this Q, we call P, then exit P, call Q, exit Q, call Q, exit Q, and exit from this Q. Now, whenever we are calling, which of the function we are calling first? At first, for the main function, we're calling this main function at first. From there, we're calling this R function. So if you see, if you try to traverse, what will be the sequence? We call this M. So we're writing, let's say, M. After M, we're calling R. So R is being called. The R exits. After that, we call Q. So we're writing Q here. Then we are calling P. So writing P here. Then we are exiting P. Then again, we're entering or calling this Q. So we're entering Q here. We're calling P again. So entering P here. After exiting QP, we are calling this Q. So placing Q here. So if you follow here, what we are doing here, we're basically traversing pre-orderly. So that means the root nodes comes first. Root nodes, like each root nodes comes at the very beginning, at the very first. However, while we are exiting or returning, this is basically what? Sequential call, only for call. Sequential calls. The first call we are making, that call is basically based on what? Pre-order traversal. But when we are returning, or exiting, this is basically done in a post-order traversal. Now, let's see how it works. Now, M, the main function, will return some value when? After the main function has been totally executed. This return function, return, is made after complete execution, isn't it? Hence, if you notice here, we enter this region, we are not returning so far, but for R, we entered, since R has no child, R is returning now. So it is returning, so we write R here, let's say, R is returning. We are over here, M has more like a right child now, so M is not going to return until the execution finishes. Then goes here, calls Q is not returning still. Q calls P. From P, there is no more calling function. So P now returns. So after that, we have this P. Then there again, this Q is not returning now. This is rather calling this Q. Again, this Q is not going to return. Rather, it is calling a P here. This P is going to return since it has no more children. So again, we're writing P. And then we are calling this Q. And this Q, since it has no more children, this will return. So we write this Q. Now, if you notice what happens, the root nodes will be basically placed at the very end. So after the traversal happens completely, that means there is no more children. It appears after the children. So in this case, let's see for this portion. Wait. After this P, we have this Q. Again, this Q won't return. Rather, we call this Q, and this Q won't return. Rather, this will call this P. So we place this. This P won't call anyone. This P rather returns. So we'll place this P here. And after this, we have, let's say, call this Q. This Q won't call any other function because this is the end. Hence, this returns. So there we'll be placing Q. And from there, we'll be having what? We'll again call this Q. And this Q has no more children. This will return. So we'll write this Q. Now, since all the children of this Q has been traversed, this Q can now return in like at the very end. So now this is for this Q. This is basically this Q. So if you see, the parent or the root node appears in the sequence when? After all the children has been traversed. Hence, after this returns, if there's no more children for this Q, this will be placed into the path. Again, it returns back. This Q won't return to this main function. Why? Because it has more children. Okay. And finally, if once we have, let's say, covered up until this much, this Q will return. And finally, this M will return. Now see, this M was the very top root, the top node. This M is returning when? After the complete execution of the path or the complete traversal of the tree. Hence, this M actually returns at the very end. So what we noticed here? We noticed that the returning of procedure or the function is basically based on what? Post-order traversal. Okay. Now, yeah, as I was mentioning, the parent of this Q, which is this Q19, until this Q ends, this Q is going to live inside the activation tree. At the same time, into the stack. Why? Because see, it is sort of related with the return keyword. Until this Q returns, is this Q, like, can this Q end its life or end its lifetime? No, because in order to end the lifetime, it has to return, and it cannot return up until all of its children has returned the values. There's no more children to be called. Okay, that's basically why we cannot actually return from this Q immediately before returning or getting return value from the children. So that means basically what? If this children or this child is onto the stack or on the activation tree, until this child ends completely, the parent will be living inside the activation tree. Okay. Now, let's try to go a bit further. We're almost there. So these informations, the information which we will be storing inside the stack, it will be in the format of record. Now, what are records? We have seen records are what? User-defined data types. So it is sort of the same thing. So we will be having now records which will be stored inside the stack. Okay, so basically what I was trying to say is this activation tree, in order to store the information, let's say for Q2, 3, those information of these parameters will be stored into the stack as record. The stack will contain information which are basically records of different functions. So that means of different scopes. These are the records which are will be stored. So in case of, let's say, let me try to redraw this because we will be requiring that. I sort of erased this portion. I shouldn't have erased this portion. So basically I have this AM, it's called R, it calls R, it calls Q19, and that calls P19, that calls Q13, and this calls Q59, this calls P13, this calls Q10, this Q23, this calls P23, Q21, and we have Q33, and this finally calls P59, Q55, Q79, this calls P79, Q77, and Q99. So this is basically the information or the activation tree. Now, this information, let's say in this case for this P2, 3, the information, not this one, let's say Q23. So Q23. So this node, before making these calls, the information of this 2, 3 needs to be stored onto the stack. Now, how do we store this information? In the form of record, because these are what? Functions. If these are functions, functions are sort of what? It's sort of like user-defined, let's say, types. Though these are actually based on or performing operations, however, these have some what? These have some scopes. If they have some scope, they have some region, they require some space. That is basically we're storing these values in the form of what? Records. Now, a general activation record will be basically following this pattern. So let me try to draw it. So the first, at the very bottom, there will be this actual parameter. So let's say from main function, we are calling this Q. Why is it not moving? Yes, it is now moving. Okay. So as I was saying, let's say from M, we are calling what? 1 and 9. Let's say Q of 1 and 9. So while we are making a call to a function, a procedure, we store the parameters here. So the actual parameters will be stored at first, actual params. So params, let's say, they will be stored at first. Then the return value, return values. Now, what are these return values? This is basically, let's say, to which point we have to return our pointer after the call has been made. Then we have some control links. Now, what are control links? I will be describing in a bit. Then we have a control link. Then we have the access link. Then we will be having the saved machine states. So saved machine status, let's say. After that, we will be having local data. That means now we are basically inside the function. So local data, and we have temporaries. Now, what are these temporaries? Remember, while generating tree address code, we introduced what? T0, T1, T2, T3, those temporary variables. So whatever temporary variables will be stored, those will be basically at the very top of the stack. Temporaries. So that means the stack is basically downwards. The topmost value is basically this one. And these are the bottom values or the inside values. So as I was mentioning, this temporary variable basically holds the temporary variables which were introduced in generating the tree address code and which were used in the intermediary stages. After that, we have local data. no, local data are basically belonging to the functions. So let's say in this case, let's see if we have one or not. Yeah, for quicksort, this is the local variable. So variables such as this I, or for this read array, that is also another I. These informations will be stored onto the local data area. After that, we have the save machine status, which is basically the, like, we are making a call, let's say procedure call. From M, we are calling this queue. Now, while we are inside M, there could be some informations. M could be in a state of adding 1,000 numbers before calling the queue function. And there could be much more declarations there. Hence, the status of the, let's say, the register flags or the register values, this needs to be stored. Because as I mentioned, let's say in main function, we are at first, we're like having this A equals to B plus C, and then we have D equals to some function 1, and then we simply do what? A equals to A plus D. So before this calling of a function, we are getting some value to A, assigning some value to A, which is this expression value of A, B plus C. And then we are calling this function 1. Now, if we're calling this function 1 and we're getting the return value to this D, and we're adding immediately after the function call A plus D or A with D, and placing or assigning this value to whom? To A. Now, if we don't store the value of this A, we will be in a great loss. Why? Because in that manner, A has been lost, then we won't be getting the actual result. Hence, here it is said, sort of being portrayed the information that we need to store or save the status of the machine. Now, the next thing is basically given here, what the access link. This access link is basically the link to the local data, which is basically required by the called procedure. So let's say from main, we're calling this function 1. So once we are inside this function 1, we might require some values which are declared inside main. So let's say, in this case, A, and we're passing this A value over here. So if this A value is being passed here, and we are requiring, let's say, int B equals to A, in that situation, we require this A to be extracted from where? From this local variable of this main function. Hence, this access link is basically giving sort of a backdoor to this function so that it gets this A using this link state or the link region so that it could get a reference to this A. So let's say this access link will sort of have a table where this resources references will be stored, okay? And then we have control link. This is basically pointing of or the pointer which points to the activation record of the caller. So main function is the caller of whom? This function 1 function, isn't it? So main is the caller which is calling this function 1. Hence, the control link is basically or refers to the pointer. This is basically, let's say, the pointer feature, the pointer to which the activation record of the caller is or present. So let's say this is a stack, like another stack or another memory location. There we have the record for this main function. Hence, what this control link is basically storing the reference to that record so that once we get or we return back from this call function, we exit. If we come to the very next line, we could pop this element once this all goes out. You can pop this element and simply point to the record which exists or contains the information of this main function. Okay, so that's basically the record is inside the control link. After that, we have the return value. Now, this return value is basically for the call functions, the call functions return value. So if in this case we are calling the, let's say the function one over here, the function one we are calling. So what is happening is this function one can have some return value. So if it is, let's say, the tree type specifier, or the return type is int, it needs to return some value. So it is returning, let's say, b. It needs to store this information or cache the information into d, isn't it? Hence, this is saying the return value, which will be returned by the function. Now, obviously, all the functions won't be having the return value. Why? Because there are void functions as well. Hence, the return space or return value won't be always utilized. And finally, there is the actual parameters. Now, why this